Hello friends, welcome to engineering tutorial. Today we are going to discuss about an important part of the communication system. So today's topic is signal analysis. So basically what we are going to discuss about is the basic concepts of signals and the classification of signals, and how many ways we can classify signals. So it is an important basic concept about communication system engineering. So let's get started. So the first and the most basic thing, what is a signal? So what is the definition of a signal? Basically, a signal is a function of one or more independent variables such as time, space, which contains some useful data or information. So generally we come across signals in anywhere in communication system which is a function of time. So it can be time, it can be space, it can be other parameters such as any other physical quantity such as temperature, pressure, and flow rate, whatever. But in communication systems, basically the involving independent variable is time. So in communication systems, all the signals, most of the signals that we will come across or will come to know will involve time as one of the variables or the only variable. So example is our voice signal, music that we hear, video, whatever. It is generally in the form of a voltage or current signal. So most of the signals that we will deal with will be in the form of a voltage or current, because only then it will allow us to process signal or to interface the signal with any other circuit, because they will only understand a voltage or current signal in electrical form. So if there will be any physical signal involved such as pressure, temperature, or flow signal, we have to convert it into an electric form with the help of a transducer, and then we have to give the electric signal to other circuitry for analysis and processing. So basically what we understand that a signal is a function of one or more independent variables. So for example, let us consider these signals: S1, S subscript 1 as a function of t and S subscript 2 as a function of t. So when I say t, it means it is a function of time. So here S1 is equal to 5t and S2 is equal to 20t are two simple signals which vary linearly with time. There can be signals which involve two independent variables. Here signal S is a function of two independent variables x and y, which is represented as 3x plus 2xy plus 10y square. You can write whatever number of expressions here. Let's say we involve another variable x, y, z. That can be also be written such as 3x plus 2xyz plus 10y square plus z. So there can be countless number of signals involving as many variables as we want, and we can form expressions with it, and it will be signals. So basically, for the sake of simplicity, I have used these three expressions. The first two expressions consist of only a single independent variable, which is time, and here two independent variables x and y involved. So it can be time and any other physical quantity such as pressure, temperature. So there can be. So basically we will come across these type of signals which involve only time for communication system. For example, a signal here is a typical audio signal waveform. Here In the y-axis we have the signal amplitude at, and in the x-axis we have the time. So here the amplitude is a function of only one independent variable, which is time. So this is a typical audio signal waveform which involves only one independent variable. Here also this is a ECG signal waveform. So ECG is the electrocardiogram signal, which is the waveform of the electric potential which is generated by the cardiac cells, so the cardiac muscles in our heart. So it is the pattern of that ECG signal. So here also the signal amplitude is a function of only one independent variable, which is time. Then we have the electroencephalogram signal. This is the waveform which is generated by the neuron cells in our brain. So here also the plot or the graph of the waveform involves the function of the signal amplitude, which is dependent on only one independent variable, which is time. So as I said, in a signal analysis we will always come across these kind of signals which are dependent on time. So these are some of the basic examples of signals that we will encounter in our day-to-day life. So then the types of signal, the classification of signal. So the signal, it can be classified in various ways. So it can be even and odd signal, periodic and non-periodic signal, energy and power signal, analog and digital signal, real and complex signal, causal and non-causal signal, deterministic and random signal. So these are 7 different ways. Well, there can be more, but basically we can categorize or classify a signal in terms of these ways. So we will discuss each of them one by one. So first let us discuss even and odd signal. So a signal which is of the form f of t is equal to f of minus t, which satisfies this expression, it is called as an even signal. Whereas if that signal satisfies this expression, that is f of minus t is equal to minus f of t, then it is called as an odd signal. Examples of even signal are, of course, cos t. We know cos is a even function, t sin t, t square. These are some of the examples. Examples of odd signal are sin t. Sin is an odd function, so of course it will be an odd signal. T cos t, t q, name a few. An important property of even signal is that it is symmetric around y-axis, whereas the odd signal, it is symmetric around origin. So here have a look. These are the examples of even signal waveforms. So as you can see, this waveform is symmetric around the y-axis. This exactly mirror images of each other. Here also, this is an even signal waveform and it is exactly symmetrical around the y-axis. So these are some of the examples of waveforms of even signals. Now odd signals. Now as I said, the odd signal is symmetric around the origin. So when you see these two waveforms, you can find that they are exactly symmetric around the origin. Exactly, if you flip it, it will completely superimpose over each other around the origin. So here, these are exactly the mirror images or opposites around the origin. They are symmetric around the origin, the odd signal waveforms. Then we have the periodic and non-periodic signal. Now what is a periodic signal? So when I say periodic, it means that the signal will repeat itself after a certain fixed period of time. Let's say it's capital T. That is called as a periodic signal. So basically they follow a specific pattern, and that pattern is repeated after the time period t. So it follows the following expression: after f of t plus capital T is equal to ft. So as you can see, the function will repeat itself after a certain fixed period of time, which is called as the period of the signal, which is denoted by capital T. Examples of such periodic signals are the sinusoidal and cosinusoidal signals. Whereas the non-periodic signal, it's obvious that it will not repeat itself after any fixed period of time. There is no specific pattern which is involved in a non-periodic signal. So, example of a non-periodic signal is an exponential signal. So, here, this is an example of a periodic signal. It's a sinusoidal signal. So, here this is a complete sinusoidal signal having a time period t. After the time period t, this waveform again repeats here. This signal, this one cycle is completed, then again it repeats the same pattern here. So, this continues after every t seconds, capital T seconds. So, this signal has a time period t. It is a periodic signal having a period capital T, because the pattern repeats itself after every t seconds. Similarly, this is a triangular waveform having a period t. This pattern is completed, it is repeated after every t seconds. Here, this pattern, this cycle is complete, then again here after t seconds, again this pattern is repeated. Okay, this is the repetition of this pattern. It continues after every t seconds. Okay, this pattern is repeated. So these two signals are periodic signals having period t. This is basically nothing but a repetition of patterns after a certain fixed period of time. Whereas non-periodic signals can be irregular. They do not have any fixed pattern, such as this signal. It does not follow any regular pattern. It's random, it's irregular. So these are non-periodic signal waveforms. Then we have real and complex signal. So it's obvious, if a signal consists of only real components and no imaginary component, it's a real signal. Example, exponential signal, sine signal, cosine signal. Whereas if the signal is composed of complex or imaginary part, or j, part involving j, or I, if you can write I, then it is a complex signal. So example is this, a to the power j omega t. It's a complex signal. Then we have continuous and discrete time signal. So basically, this is a continuous and discrete time signal. So here the parameter t, which is denoted or which is represented in x-axis, it is a continuous parameter. It means the basic difference between continuous signal and discrete time signal is that in continuous signal, the amplitude values or the ft values at each and every point of time are considered. Okay, the amplitude values at each and every interval of time is considered, whereas in discrete time signal only the amplitude values at specific points are considered. You see the black dots, these are the points where the amplitude values f of n is considered, and all the other points which are normal are not considered. That is the only disadvantage of discrete time signal, because there is a loss of information, because we are not considering the points between these black dots. The amplitude values are not taken into consideration. Basically, this technique is used for analog signal to digital signal conversion by a process called sampling, which we will discuss in some other video in detail. So this process is basically called as sampling, where we take the amplitude values only at certain specific points for converting it into a digital signal by a process called sampling following the Nyquist criteria. We will create a video on that topic specifically, but for the time being you just understand that in discrete time signal only the amplitude values at certain specific points represented by these black dots are considered, and all the other points, the amplitude values at all the other points are not considered. So here the time t is a continuous parameter. Here the discrete time interval, or the points where the specific points are represented by the discrete time interval n. It is discrete, it means it is distinct. The points are distinct, different from each other. That is the basic idea between continuous and discrete time signal. So then we have is the deterministic and random signal. So a deterministic signal is one which is regular, and the amplitude values can be determined at each and every point. Okay, we can at any point of time we can determine the value of such a signal, whereas a random signal is one which is highly irregular, and we cannot at any point of time we cannot determine the value, the amplitude value of the signal in terms of a function. A deterministic signal, all the above signals which we have discussed until now, they fall under the deterministic category because they are defined by a function. Exponential signal, sine signal, cosine signal, whatever, ECG, EEG. But the random signal, for example, the basically the biomedical signals are random in nature, the ECG, EEG signal, whereas the other signals such as sine, cosine, the exponential, they are deterministic because they can be defined by a suitable expression, whereas the biomedical signals or the thermal noise signal, they do not obey any fixed expression. So they come under the random signals. Okay, the values cannot be defined at each and every point of time, they are irregular, whereas the deterministic signals, the values or the amplitude values of the signal can be determined at each and every point of time. Okay, then we have is causal and non-causal signal. Now a causal signal is one which does not exist for negative time intervals, that is for time t lesser than 0. So it can be expressed as ft is equal to 0 for t lesser than 0, all the negative time intervals. Whereas a non-causal signal does not satisfy this condition, the causality condition. It's basically a futuristic signal. So this is the causal and non-causal signal. You can note down all these things if you want, because they are given side by side for easier understanding. I have given it in a comparative way. So then we have is an important classification which is analog and digital signal. This is the most important classification of signal, analog and digital. Okay, an analog signal is one which can take infinite values of amplitude of the signal. The amplitude value or the amplitude of the signal can take infinite number of values. Okay, there is no limit to it, from 0 to infinity. The amplitude can be anything, whereas the digital signal has only two values which are defined by two voltage levels which are represented as logic 1 and logic 0. They are defined by fixed voltage levels. So the analog signals can take infinite values of amplitude, whereas the amplitude of digital signals have only two values which are defined by logic 1 and logic 0. Of course, as it can take infinite number of values, it is continuous, but digital signal is discrete. As I said, in discrete time signal is constructed by a process called sampling, which is a part of analog to digital conversion. So the digital signal is discrete in nature. the points at which the amplitude values are considered at discrete, which is taken in the sampling process. So, the analog signal is continuous in nature, whereas the digital signal is discrete, it is distinct. Now, as the amplitude value can take infinite values, analog signal is more affected by noise and interference, whereas the digital signal, as it only considers two voltage levels, two values, it is less affected by noise and interference. Because of the same reason, power loss is more in analog signal, whereas power loss is less in digital signal, because it only considers two voltage levels. Now, storage of data or analog signals is very difficult, whereas digital signals can be stored easily. So, these are some of the important points which are related to a distinction or a comparison between analog and digital signals. So, here an analog signal, for example, we have considered a sinusoidal signal. It is continuous in nature. So, it can take the amplitude can take any value in between 0 and infinity for an analog signal, but a digital signal has only two values, two output values, logic 0, which is defined by a certain voltage level, let us say it can be 0 volt, and another value represented by logic 1 is represented by another voltage level, which is, let us say, plus 5 volt. Okay, this is the general convention. It does not mean that it is always 0 volt and 5 volt, it can take other values. Just for the sake of understanding, I have mentioned these two values. So, it can take only two values, 0, logic 0 and logic 1. So, this is an analog signal, this is a digital signal. Here the amplitude values can take any value, but here the amplitude has only two values, logic 0 and logic 1. So, lower level, this is the higher level. Then we have an energy and power signal. Okay. An energy signal is one in which the total energy of the signal is finite. It is a non-zero value lying in between 0 and infinity, but the average power of the signal is 0. This is the main criterion for an energy signal. So, it satisfies the condition that the energy of the signal E lies in between 0 and infinity, whereas a power signal is one in which the total energy is infinite, but the average power is finite. It has a certain non-zero value which lies in between 0 and infinity. The power value of the signal, the average power value of the signal lies in between 0 and infinity. Here, if let us say Ft is a continuous signal, then the energy of the signal is given by integration of modulus of Ft square from the limit minus infinity to plus infinity, which is Ft square dt, whereas for a discrete time signal Fn, it can be written by this same summation of Fn discrete time signal square modulus square from lower limit minus infinity to upper limit plus infinity. This is for the energy signal. Then for the calculation of energy, then if we want to calculate the power from the continuous time signal Ft, then it can be written as P is equal to limit t tends to phi 1 by t minus t by 2 to t by 2 integration Ft square dt. So, we know power is the rate of change of energy with time, the rate of dissipation of energy with time. So, basically here we are dividing the whole expression with time with limit minus t by 2 to t by 2. P is equal to E by t, that is the basic principle which is involved here. Now, for a discrete time signal, power is given by limit n tends to phi 1 by 2 n plus 1 minus n capital N to plus n f n whole square. N is the discrete time interval. Here t is the period of the signal for a continuous time signal and n is the discrete time interval for a discrete signal, capital N. So these are some of the basic concepts which are related to energy and power signals. Now all these concepts which I have mentioned about various types of signals, they are not given in detail, they are just given in terms of bullet points, so that you just have a basic idea of what a signal is and how they can be classified, what are the various types, just to give you a basic understanding about it. We will discuss about each of them in detail in the upcoming videos. So just for a quick brush up, a quick look at about the basic concept of signals, I have given this video so that we just know what a signal actually is and what is the basic definition of a signal and how it can be classified in a number of ways. So please subscribe my channel Engineering Tutorial for more such videos related to communication system, electrical, electronics and instrumentation engineering. Have a great day. Thank you very much.